And our first presenter is Darren Highfill. He is actually an S4 alum, but this is his first time on the big stage here. He is founding and managing partner of Utilisec. It is an electric utility cybersecurity consulting firm. And he also has done a lot of work for Southern California Edison, Department of Energy, and if you talk to him, he's very, very involved in all sorts of smart grid standards and recommendations and guidelines efforts. So we'll get him, are you all mic'd up?
Check, check, yep.
We'll get him set.
So yeah, I'm wondering how much credibility I just lost by being in charge of security for smart grid. No, seriously, thank you very much, Dale. I've really enjoyed coming to S4 over the years. Anybody that I've talked to about S4 will know that I'm a big evangelist of the venue, and really look forward to coming here to this opportunity. It's a fantastic thing. So thanks, Dale. Keep doing what you're doing. Taking some inspiration from Dale's opening remarks, this presentation is not as much down in the weeds as an awful lot of the presentations that I know you're going to hear today and tomorrow. This presentation is actually about justifying the high expectations that Dale was talking about. The requirements that folks go to their managers and say, this is what we need to build into the system to make it secure, to make it work. So this presentation is actually about those requirements, or what I will call controls, during the course of the presentation. Now, the presentation title, Witch Doctor versus the Engineer, a little bit of kind of poking a little bit of fun here, and my, quote, friends, unquote, wanted me to come to the presentation dressed up as a witch doctor. And I have to admit, I could not quite bring myself to do that. Figured I had enough of a challenge getting you folks to take me seriously when I'm up here talking about requirements. But ultimately, we've got to have something to build to, especially if we're ever going to create a secure infrastructure. We've got to actually know what to ask for. So I'm going to start off by talking about just some definitions to set some, set the table here. When you look up witch doctor, one of the first definition that you come across, a shaman or a medicine man, somebody that, especially in pre-literate societies, appears to possess magical powers, especially used to cure sickness, but also to harm people. So there's some parallels here. Curing things, inoculating ourselves against evil things that can happen on our systems. If you want to dig into how a shaman is defined, it's very similar. A person who acts as an intermediary between natural and supernatural worlds. So you'll also see me draw some parallels here as to some of the work that we do later on in the presentation. I'm also going to talk a little bit about tribal knowledge. Basically, knowledge that is not commonly known by everybody within the organization. It's usually used to reference information that may need to be known by other people, but is not necessarily readily available, may be required to build a product or service. It also may be really important, that information may be very important to the quality of the outcome, but it could also be totally incorrect. So let's flip hats a little bit, talk about what's an engineer, person trained or skilled in design, construction, use of engines or machines. Engineering, the art or science of making practical application of the knowledge of pure sciences, such as physics or chemistry, and putting that science into real-world use. If you look at how science is defined, a branch of knowledge study dealing with the body of facts or truths systematically arranged. That's important here. Truths systematically arranged and showing the operation of general laws. All right. So let's go ahead and do a little pop quiz here. See if you actually paid attention to Dale's opening remarks and what I've thrown up here off the bat. I'm going to show you a series of pictures, and I want you to tell me, am I showing you a witch doctor or an engineer? And just in the interest of time, don't bother writing it down. Just as soon as you recognize, as soon as you figure it out, tell me, okay? Say, that's witch doctor or engineer. And by the way, valid answers are witch doctor or engineer, not, hey, that's Fred. So, witch doctor or engineer? Engineer, okay? Come on, folks, wake up. All right, so we're off to a rough start here. Witch doctor, all righty. Witch doctor or engineer? Engineer, okay. Come on, folks. It shouldn't be that hard. Witch doctor, all righty. Witch doctor, okay. A little more questionable. All right. So let's go with engineer. Witch doctor, all righty. Witch doctor, all righty. Engineer, all right. Witch doctor, engineer. All right, so I think you guys are starting to get the hang of this. And this one's actually my favorite. Noticing that the nice little dollar sign around them, and if you, in case you can't read it, these things hanging off of them here say Ritalin and Prozac, and this was on a greeting card that you open it up and it actually inside the greeting card said next. So. Anyway, alrighty, so getting back to the theme here, black magic, a lot of security practitioners, and I've been guilty of this too, a lot of security practitioners like to do their math in their head. They take in the input, they internalize it all, and come up with a set of controls that they recommend based on their knowledge and experience. But they don't necessarily document exactly why they chose one particular control or how it satisfies the requirement. The answers that they give are still defensible. If you ask them to defend one particular control or requirement that they come up with, they can tell you why. But the analysis took place all in their head. They didn't necessarily actually jot down all of their homework, which makes it not easily repeatable for somebody else to come along and produce the same or similar results, or to even analyze the results. So I hear a lot of folks talking about doing security engineering. And this term, I think, is getting abused a fair amount because in a lot of cases, there's a critical element of engineering missing here, specifically the application of scientific principles. If you look at the scientific process, basically what you need to do is you need to find the causes of success, or more usually a failure. Actually build some kind of hypothesis around why that happened, methodically test that hypothesis, and then publish your results and make it open for review so that anybody can come back and look at what you did and figure out if it holds water. So I'm going to poke some holes here at a document. This presentation is actually kind of a complement to the paper that's available. The paper digs a lot more into what actually constitutes quality controls or good controls, what constitutes a good process and whatnot. I'm actually going to pick on NIST 800-53 because it is one of the documents that's actually one of the most referenced in the industry. I've actually referenced it a number of times, and it's what a lot of folks would consider best practice in the industry for coming up with security controls. It's a pretty structured document. It actually references FIPS 199 and FIPS 200, saying, okay, you use FIPS 199 to come up with what you're going to protect and why. FIPS 200 to determine already how much protection do you need, how do you need to go about protecting that, and then you go through a process, a pretty well-documented process of selecting baseline controls and customizing or tailoring those controls. But where were the recommended controls actually composed? How were they actually composed? I have not been able to find any documentation that said, here's how we generated this control. The controls are just kind of presented as this is what we think, tackles the stated problem. How do we know that the controls sufficiently mitigate the targeted risks? How is there any kind of evaluation done of, this control satisfies this or is sufficient to cover this because of X? What are the controls actually linked to? Are they linked to threats, vulnerabilities, failures? Are they linked actually to risk? I've got a hypothesis that the controls are actually linked to the objectives as delineated in FIPS 200. Actually, that should be FIPS 199. Because if you actually look at the organization of controls in 800-53, they map pretty closely to what's in FIPS 199. But there's no actual statement that says, here's where these came from, here's how we came up with them. So from my standpoint, there's really not a pedigree here for the control composition. Did they come from lessons learned? Did they come from experiential data? Did it come from some other documentation? I suspect that there was actually an awful lot of very skilled, very talented people that worked on this document to produce these controls, and I don't want to slight their capabilities or intelligence, but at the same time, I don't know what they used to come up with the controls. So it's impossible for me to go back and examine, okay, was there any human error in this mix? How did this come to be? Would there have been another option or another choice here? So again, no basis to determine adequacy or sufficiency. How do we know what's justified? There's no real way no effective way to link the controls to system functionality. There's ways to link the controls to security functionality, but not to system functionality. There's not a way for me to go in and say, Artie, I'm in a chemical plant making Play-Doh, and so I need to have controls that do X, Y, and Z versus I'm an electric utility and I need to implement a substation, and therefore this substation needs to have controls A, B, and C on it. I don't really have a way to differentiate that beyond the security functions that I'm trying to accomplish. So there's also no means in the document that I can find to generate controls that prevent the system from turning on itself. And what I mean by that is if you put all of the security controls on a system in the world, that still doesn't prevent the system from a design standpoint from being able to be turned and used for ill gain or maliciously, or basically turning the system to destroy itself. This is some engineering functionality that has to be associated with the actual system itself and is not the kind of thing that you're going to find in broad guidance. So now I'm going to shift gears and start talking about my research. Specifically, actually, it's the Department of Energy's research. Thanks very much to Carol Hawk and the others at the Department of Energy and the sponsors in industry, such as Southern California Edison, that have supported this project. The Advanced Security Acceleration Project for the Smart Grid, or ASAP-SG, has been a collaboration between a group of North American utilities and the Department of Energy to develop system-specific requirements for pieces of, quote, smart grid functionality. There I go, losing credibility again. So these are the different pieces of functionality that we have either done so far or at least had scoped out. AMI, third-party data access, distribution automation, synchrophasers, I'll also call that WAM. You'll see a reference to WAMPAC, or Wide Area Monitoring, Protection, and Control. That's synchrophasers. And substation automation is what we're working on now. We had originally scoped out a profile for home area networks, but it's questionable whether we're actually going to be able to get that one done at this point, because we're having trouble actually getting private sector funding to fund that project. So I'm going to dive into and give you kind of a history of how we got to where we are with ASAP SG and how we got to the development of the process. The first security profile that we developed was for AMI, and we were just as guilty as anybody else here with the NIH not invented here syndrome. We said, oh, you know, it's a brand new domain, we must therefore need to go reinvent something. So off we went. We did come up with, or we did very much build out something called, a concept called security domains that we actually borrowed from some documentation in a project called the IntelliGrid project, or ICSA project, if you're familiar with the electric power sector. That IntelliGrid is kind of the precursor to what a lot of folks started calling the smart grid. In terms of how we generated the controls, we actually just took every bit of best practice guidance that we could find everywhere and dumped all of the controls into one big bucket and stirred them up and then kind of sorted them all out and said, all right, what security controls come out of here and how can they be merged and normalized and resorted and renamed? It was a big mess. So the bottom line was what came out of all of it was, you know, the controls that we selected, they were based on our team's experience and judgment. You know, we had what we thought were a bunch of smart people gathered together, and when somebody said, well, why'd you pick these controls? Well, we're smart people, trust us. You know, how familiar does that sound to you? So the interesting thing about going and doing something first or throwing something out there is that if it has any weight to it at all, you'll immediately get people coming back and asking you why. You know, okay, we asked you for security requirements for AMI. You came up with these. Why these? Why these particular controls? Or these controls look really, really onerous. These look like a real pain in the butt. You know, why do I need to implement all of these? Why do I need to actually go to my manager and try to convince my manager that I've got to build all of these into the system? Which ones are more important? Can you give me a short list? So that started really pushing us as we developed subsequent security profiles. With the third-party data access security profile, the first thing that we did actually was add in use cases. This was really just as much to help us wrap our own heads around what third-party data access is all about. And I won't derail this presentation with all of that detail, but if you corner me at the reception this evening over an adult beverage, you might pry it out of me. But the bottom line was that we actually used use cases to capture the system functionality in the document that we created. From a control generation standpoint, we actually used the DHS catalog as a baseline. The DHS catalog of control system security, which is in turn based off of 800-53. We added controls and tailored controls as we saw fit for the system, but bottom line was that the judgment was still, the selection of those controls and what they applied to was still based on the team's experience and judgment. So for the third security profile that we did, this is where I think we finally actually started to get some traction and started to bring something serious to the table. We added a failure analysis to the equation. This was the first effort, as it says, to provide a tangible binding of the controls to the system functionality. So what we did with the failure analysis was we captured the use cases, and then we went step by step through each use case and said, okay, how can this system fail at each one of these steps? and therefore we use those failures then to prompt and justify controls that we selected. So we were still using the DHS catalog as a baseline, added controls and tailored them as needed, but now we actually had some justification for selection of those controls because we were basing them on mitigation of failures. The next security profile that we did, WAMPAC, Wide Area Monitoring, Protection, and Control. This is also a reference to synchrophasers. We refined the failure analysis because when we actually went through the failure analysis the second time around, we found that about 3/4 of the failures that we came up with were the same as they were for distribution automation. So we realized these are actually a pretty common set of failures that are going to be found in most systems. But then there were maybe about 1/4 of the failures that were unique to the system. That this is a failure that's related to how synchrophasers work and has nothing to do with how distribution automation works or vice versa. We started to build this library of failures that we started looking at. We refined our network segmentation recommendations. We took a little bit different approach to controls this time. We actually used the DHS controls as inspiration, but then we came back and we rewrote every control that was in that document. We wrote it from scratch saying, what does it mean to implement the DHS control in a synchrophaser system? How would I actually go and satisfy that DHS control in a synchrophaser environment? So again, the selection of the controls was based on the mitigation of failures. So now that brings us to current day. We're working on the substation automation security profile. The interesting thing about substation automation is that the number of peer-to-peer communications between the different roles in the substation actually is through the roof as compared to any of the profiles that we have done before. In other words, if we tried to capture use cases that described everything that could happen inside of a substation, we would have easily over 100 use cases using the same methods that we had used for previous security profiles. So that was not really going to work for this approach. So, all right, one hurdle encountered. How do we actually, that was one of our foundation pieces. So how do we actually address the system functionality for substation automation? So we've settled on actually using a combination of state transition diagrams and zonal analysis. So zonal analysis, again, you'll have to, this will be adult beverage number 2 that you'll have to corner me with. I'll tell you a little bit more about what we're using on that front this evening if you like. But the interesting thing here, because I think it starts to lead to some of this scientific evaluation, scientific analysis of security, is the state transition diagrams. So what is a state transition analysis? We start with looking at the high-level process flow. Then for each of those steps, we analyze the possible system states and how you actually transition between them. The state variables that we define actually represent the system conditions, and they change in response to system events. And then we actually create a truth table to determine what the resultant state is and evaluate that state. Is it a failed state, or is it are you in a vulnerable state, or is this actually a legitimate state? So this is an example of what a high-level process flow looks like, and I realize this is way, way, way too small for anybody here to have a reasonable chance of reading it. The one thing that I'm going to point, I'll read through so you have some idea of what this is. Receive input. Is the source validated? If yes, then is the message current? Then the source, is it a sensor or an application? If it's a sensor, then receive the data, record the input. Is action needed? If yes, then what type of action? If it's data, then change the data point. If it's a control or the source was an application, then you receive the control, or you take that action, you compare the results to the system state, and then no likey is how you dump out of the system down here at the bottom. But the one I'm going to one I'm going to focus on here actually is this first step here, receive input. So we'll look at what an idealized subsequence would look like for that receive input. You've got the substation bubble up here that actually is external. That sequence flow that I just went through is actually for a control application issuing a command to say a circuit breaker to open. So this would be the substation as external to the system that we're analyzing here, as external to the control application, pushing some kind of data to the system to say you need to operate. Well, that control application then receives the input and it does something with it. Data receive notification sends it, on to push data onto the stack, and there are some loops here where it loops back in to wait for the next receipt of data. So we go through and we actually define a set of variables here to describe what the states are and how those states interact. For data receive, this can be either true or false. It basically represents have you actually received the data. For data present, if you look in your hands, do you actually have data on hand? Data receive notification, true or false, being you actually send back out that notification that you've received the data, and then push data onto stack is whether you have actually pushed data back out of your process onto the process stack. So then we go through an actual state transition analysis where we look at a truth table here of all the different combinations for the different variables that are defined and what the end state is projected to be for that particular combination of variables, and then some remarks about whether that is a valid combination or a combination that's desired or not, whether it's vulnerable or not. So you wind up with a state transition diagram where receive input and circling back into receiving input is actually the only secure or safe state here. All of the other states here, state 1 here, it says data present but no recognition. In other words, you've actually got data on hand, but you don't realize that you have data on hand. State 4 here is no data present, but notification is passed. So, in other words, you sent out notification, hey, I've got data, but you didn't really have it. The other state down here, data present, but failed to receive. So that would mean that somehow or another you came up with data, but nobody sent you anything. That's probably an indication that it's a problem. And then all of these different paths are ways that you can navigate from one state to another and how that takes place. And those actually wind up representing failures and failure modes. So there's really only one here where you keep winding up in that same state where you can receive data. Remember, I'm still talking about that first bubble in the process. The whole point of that bubble is to receive data. So as long as I'm in that state, I don't have a failure. It's an acceptable system state. S1, okay, something's gone wrong. Actually, S1 process is in complete failed state. Data is present but no recognition, from maybe a network cable being unplugged. And we go through and we actually look at each one of these transitions and the possible causes, basically the failures and the failure modes. So, having gone through all that, and we're still in the middle of that process, I don't think we're there yet, in all honesty. I don't think we're all the way to the point of being able to scientifically say we have come up with, the complete answer here. We still don't have an empirical link demonstrating that a control that I pick mitigates a specific failure. I'm getting closer. I've actually figured out, how to really quantify the failures, and I think we're putting ourselves in a position to be able to define some controls that can be empirically evaluated, but we don't have that link just yet. So we're currently limited by inductive logic, basically saying well, this control looks like it should fix that problem over here. So now I need to form that hypothesis and go and test that theory and see, does that hold up? So there's some rhetorical questions here. Can a control actually be shown to mitigate a failure? Or can it be proven to mitigate a failure? And these are questions that I would love to hear your thoughts and feedback on here in the Q&A. Can a test actually be devised to verify proper implementation of a control? In other words, I specify a control that I think should mitigate a failure. How do I know that you actually implemented that control properly? Can you legitimately test that control to find out, hey, it was implemented the way that it was designed? And I've actually got a slide here in the deck to talk about just who Utilisec is. But Dale, I don't know, are you planning to make the presentations available? Videos available. Okay. So with that, I'd like to take some QA. First tomato.
And let's maybe go back to the question slide too, just in case anyone wants to tackle those. So yeah, just we'll get as many people in as we can and introduce yourself.
John Smith, Acme. Zach Tudor, SRI. So I would say no and yes, but your terminology is off for us here because a failure in a protocol is different from a security event or exploit, right? So, can the control be shown to mitigate someone attacking you? No. Can a control be shown to mitigate the failure of the protocol? Yeah, probably so.
Interesting point. I would actually, I didn't cover how we actually wound up focusing on failures in our process as opposed to threats or vulnerabilities. One of our motivators there was that so many security attacks, cybersecurity attacks, are so elaborate and take such a circuitous path to get to the end goal that we've found that trying to tackle that at the movie plot syndrome level was impossible. There's just no way to go form that wall. So our motivation was actually to follow basically a similar path to what a lot of security researchers do, which is dive down into the minutia, the really small. Travis Goodspeed, who's not here this year, unfortunately, but he's a great example of somebody that dives down into finding some little tiny itty bitty thing that he can twist and turn and use that to pivot and launch the attack. So that's the level where we focused our efforts, and basically we abstracted the problem to a point where that attack, in order for the attack to be successful, the system needs to fail at some point in the process. That's our hypothesis. So we have focused on the failures of the system, and that being how an exploit or an attack is actually manifested.
Other questions, comments? I'll throw one out there while I'm walking around. Can you give us, this might be an unfair, but do you, off the top of your head, can you think of an example of a DHS control and how it was rewritten for one of your standards? I mean, even if it's not quite exact, but just the type of rewriting that you did? Yeah, no,
I've actually got a slide or two that speak to that in another deck. But generally, a DHS control might say something along the lines of the system encrypts data as it's passed from sender to recipient, but it doesn't say how or what the specification is or anything along those lines. And so we drill it down to the next level and say for substation automation, we might actually put a link in there to IEC 62351 and say the system shall implement, it shall encrypt and a message, or say it must digitally sign a message, going from point A to point B, and actually define those points relevant to the system context at hand, and point to a specific type of technology that would then be used to satisfy that higher level control as specified in DHS.
Other questions? I stole Sean's question. I just happened to have a mind meld there.
Hi, Jason Reeves, Dartmouth College. So my question is, it's kind of a comment question, I guess, but the problem we see with security a lot is that there are really no metrics. There's no way to define and say with a lot of certainty, well, this is going to make us more secure. Taking this action is going to be, we're going to be better off for doing it. So that, I think that's why a lot of people kind of go with, gut instincts or experience, because there's no way to say it empirically. How do you work around that with automation or with system automation here?
Well, actually, the approach that we've taken, that's one of the biggest motivators here is justifying controls, is saying, why do you need a certain control, or why do you need a certain level of control? And by tightly binding the controls that we select to the system functionality, we are saying it's this piece of system functionality that prompts the need, that it has the potential to exhibit these failures, and therefore prompts the need for this set of controls. So it actually puts the conversation back on the business manager to say, hey, well, I can't afford those controls. Well, then maybe you shouldn't be doing that bit of functionality, because this bit of functionality requires these controls. So, if you don't want to do those, then maybe that functionality isn't worth the risk, and you want to roll back out of that bit of functionality. So it binds the controls to the functionality rather than making an arbitrary assertion of this is a sufficient level of control assignment.
Hi, Andrew Ginter, Waterfall Security Solutions. It's a truism of the security world that you are never completely secure. It's not a binary state. It's never yes, I am, here I'm done. And so it seems logical that if you define a bunch of requirements like this, there must be use cases that you run across and say, we're not going to address that use case. These requirements can't address that use case. There must be use cases like that. Do you document them? Does that make sense to be part of your deliverable, saying here's what we addressed and here's what we didn't?
Actually, yeah, that's an excellent point. And we do address that, I believe, to a fairly strong degree with our explicit scope statement in our security profiles. We pretty thoroughly go through and we say, already, here is how we define the scope for what this security profile addresses. Here is explicitly what is in scope and what is out of scope. And then we actually propose for each security profile, we propose an abstract communications architecture with abstract roles defined in it. And then we go through and do a mapping of those abstract roles in that abstract communications architecture to real-world examples, to say, already, here's where you find a relay application, or I'm sorry, a protection application versus a control application versus a monitoring application. You may actually have all three of those abstract roles implemented in one device, but that would actually just mean that you had to satisfy all of the controls for all three. So we go through and we try really hard to actually describe, here's what we are covering in terms of the roles and the functionality and the scope of the system, and try to state that in terms that are very tangible and understandable to the target audience. We try to frame it up in the language of the target audience.
I'm Eric Byers, and I'm Chief Technology Officer for Tofino Security. First of all, I like the concept you have here about making this an engineering discipline and maybe a little less witch doctory. So, I have a couple of questions, but the first one that I wanted to ask was, do you think you actually pick up some of the edge cases? And I'm thinking of things like the recent revelation that if you put in special characters into your password in certain Siemens equipment, it would reset it to, I think, 100 or something like that. It was a trivial password. I mean, would that ever show up in your state diagrams?
Where something like that would show up in our state diagrams actually would be on validation of input. So we would absolutely have, after receiving input, after the receive input state diagram, the first thing you do is you start processing that input. Well, that's going to be, I mean, ultimately this is an enormous chunk of work, the state diagram, state transition analysis. And we've actually given some thought to if we can ultimately build this huge state machine, you know, modeling it is going to take some serious horsepower. But one of the next steps would be, all right, you actually received input, now you have to process it. You know, part of that processing is validating that it is legitimate input. And so that hopefully would be something that would be caught if you put in, you know, illegitimate input, or if, heaven forbid, it was actually designed in there. Well, then actually that would be caught in, you know, in the design spec if it's appropriately captured in the use cases. When somebody goes to map up their, you know, their design spec against the use cases, it's going to come out in the wash where there's ultimately a gap between how we describe how the system works and how they have implemented it.
Yeah, I had another question. Say a little bit more about this zonal modeling.
Alrighty. Yeah. Alrighty. So I should have actually thrown a diagram in here and then hidden the slide in order to bring it up. But for the substation automation zonal model, we actually have about 4 tiers of roles. At the very bottom, you have the process bus, and you have an actuator and a sensor are the 2 roles that sit on the process bus. Coming up from there, you go to the station bus, and you have protection application, control application, monitoring application, and I think there's one other role that I'm forgetting on that one. The next step up, you've got it's equivalent to an HMI, but it's the operator interface. You've got a substation gateway or a proxy, and then stepping on up from there, you've got your control center or other substations. So we build this model, you know, connecting. It looks somewhat like a network diagram, but it's using abstract roles instead of actual components connected to these buses. And then we actually draw perimeters around, they're actually overlapping perimeters around the different roles to indicate what functions they're involved in supporting. So where this came from is the idea of if we thought about the substation as I'm in a hot air balloon, and I've got to start throwing stuff out because I'm too heavy. I'm going down. The first stuff I'm going to pitch is my connection to the control center and the outside world and so on. The next thing I'm going to pitch are my operator interface panel and the substation gateway or proxy. The next thing I'm going to pitch are my monitoring applications and my control applications. The last thing I'm going to hang on to are the protection applications and the actuators and sensors. And so that then describes one perspective or one view of a zonal analysis. There are other use cases that prompt other other organizations and other structures. And the way that we'll work this into controls is by combining the state transition diagram analysis that we talked about, which really talks about what happens inside one of the roles. We'll combine that with use cases where one role is talking to another role, and what zones does it cross, essentially what security domains, what security assumptions and security requirements do you change as you migrate from one zone within this architecture to another zone.
Mike Tucker from NextEra Energy / Florida Power and Light. One of the questions I had when we were going through this is that things are getting more and more complex. Right? Things have got more and more features, especially security features. There's a larger code base. There's significantly more complexity in our operating systems and in the software that actually runs control systems in and of itself. How does your approach resolve this how does it deal with this ever-increasing complexity in a manner that allows it to continue, building this catalog and having it in a way that you can actually work with it, that it's not expanding as faster than the universe is expanding?
Right. Well, let me be clear in that we don't solve the problem of an organization deciding arbitrarily that we need to build more and more functionality on continually. That's a business decision, not not a security geek decision. How we do bind to that though is by this very explicit capturing of the system, of the assumed system functionality. So we go through, I think, a lot more effort and detail than most of the other processes that I've seen to actually say, this is what we're assuming the system does. This is the assumed system behavior for this set of controls, and documents it very thoroughly, very exhaustively. If you then, at a later time, come back and add functionality to the system that you've implemented, if that functionality is represented in our model, then great. You've already got the basis there. If it's not, well then, at least now you've got a basis to figure out, okay, well I can follow the same process through to analyze the additional functionality that I want to add on. And it also provides a traceable path by which you can figure out, here's what that change, what kind of impact that change has on my understanding of the system and the requirements at hand and what controls I've implemented. Run it back through.
Great. Thanks a lot.